So basically, we kind of establish our understanding on the double integrals when it is the endpoints, they are all constant. We can basically integrate and we can switch the order of the integrations easily, no problem at all. We can even separate the function. If we can separate, if there are perhaps there are two variables, we can separate these functions as well. If we can separate it according to the constant in the variables, right? But what we have in the subject, okay, in the next part, is we are not going to have only for the endpoints that is a constant, but we may have a generalized region. So we call this content or the topic will be the double integrals in the general region. So this is what this looks like. Okay. So first we need to establish, okay, because what we have in the previous introductions on the double integral, we have the rectangle, right? We have the rectangle that is cut by like small pieces. But the problem is over the time, what we are going to evaluate is something that is maybe in terms of curve, not in terms of exact rectangle, right? So we might need to have a new way to restrict the region. Okay? So if we have this D, and we define that we are having R as in the rectangle set, our usual integrations. And we have D, which is our general region. So we could define that we have another function we call the capital F. This one, the top one. So suppose that we have this capital F defined as a piecewise functions of this small f, that function that we're supposed to know beforehand. And then the other one is the constant zero. Okay. So if it's on the region D, it will be fxy. But outside of D, in the R, then we say the function will be zero. Okay. So this will be valid, and we can use these definitions to form our integrations. Okay. So then we could say that because of the definitions from the piecewise functions, we can say that the double integral of the surface function f on the domain or the region D, it will be equal to the double integral with the R as a region of the capital F over the area. Okay? So this will be our first step to understand how to compute. Okay? The next step is more practical. This is basically the definition and some setup. The next step is more practical. So basically, we could set the graph of f into a restrictions that is going to be easily recognized. Okay? So for example, if we have something like this, so suppose that the D can be either the first picture, second, or the third, but we need to introduce another function, which is G, which G is a function of, in terms of x. Okay? So we could use this function G, and we can have, for example, we can have like a two curve in between, and we know that the curve will be in terms of x. So that means we can use this when we have the integration with respect to y. Okay? So let me write here that we can have the let me just write D equal any xy when the x is from A to B constant,
but y is function of x. Let's say g1x and g2x. And of course, we need to also establish that this g need to be continuous. Okay? So g1 and g2 continues on the interval AB. So we need to have this in our region. Okay. So then we can evaluate basically based on,
I think if we remember the rectangle that we have, we can bring them to this D, and then we are going to use directly the restrictions between this G1 and then G2 for Y, and for X we can take the AD. So we can definitely
use these definitions.
So we are going to set up this double integral. So when you are going to see the variable is x, okay, it starts from a to b, so that will be a constant. We are going to set the constant in the outside integral. Okay, so we are going to set this in the outside integral, where the y will be the inside, because y will be a function of x. Okay, so this will be the the basis foundations for double integrals for more to come. So every time you have some curve that is a function, then we can set that in the inside, and then the outside will be a constant. It will be the same also for if we have triple integral. It's much more complicated, but the outside integrals, it must be constant. Okay? It must be constant for definite computations. Okay? So suppose that if we have another applications, okay? Suppose that not this function of x, but how about if we have x equal function of y? That means we are going to change the order. We're going to have the x dy, y as a constant, and for x it will be a function of y. Okay? It could be with the similar perceptions and similar definitions. Okay?
So I think to understand from previous theorem, if we could see, so to evaluate, so let me write just some notes here. So first choosing rectangle that is defined by R, and this is the dimension, and R contains D. Okay. And we have the capital F as the same definition as in the early introduction. So we can have the double integrals. This will be equal to R. This will be equal to, suppose that we have the, this is A, B, C, D. This is capital F, dy, dx. Okay. So we can observe that based on definitions, based on definition of F, so F itself will be 0 if y is outside of the D, or we can say it's less than g1 of x, and y is greater, or not and, it's supposed to be or, g2, okay? So therefore, the inside integral of this fxy dy, this becomes this is basically just a definitions to help you connect the idea from the previous discussions. And this equal to so thus the definitions, these definitions will be true. Okay. Okay. So why we need to have this? This is basically the basis, or how to define from the double integrations what we did in the rectangular shape. What if we have some general region like D, and if we could have D restricted in a way that this curve is a function of x. Suppose that we can limit the D in terms of x, or y equals something of x. Then we could use the definitions of the capital F, in which all the points outside the D make the F is 0, which means that the inside integral, because the outside is 0, then we need to only compare, or we need to only compute the inside one, which is restricted by this curve. Okay, so because of this, and this is back to the first definition, this will be equal to the f, the small f, then this will be true, then we can write this in terms of this double. Okay, so that's basically the definition. So we start from the rectangle, and then we have something general inside. Okay, it could be defined as this type, or later, after this page, we can see also another type, which is a function of y as well. But I don't want you to confuse a bit with the terms, like function of x, function of y, because it could happen in any random way in the problem. So I don't want you to focus like you have a problem, oh, what is this function of x, function of y? No. I believe one way to solve this is to understand the functions, to understand the area of the region. Okay, so basically that's how you can solve the case. Sometimes we don't need to visualize, fully visualize in 3 dimensions. As long as we can draw easily this area, projection of the surface, we could compute easily, and we can compute easily. So that means understanding the area of the integrations will be important. Okay? Understanding which one is the functions that is going to restrict the region, that will be important. Sometimes you can work with function of y, sometimes you can work with function of x. Sometimes both will be okay to go. Sometimes one way may be a little bit complicated, the other one may be easier. So it's also depends on our choice. Okay. Okay, now the second part here, we can also have this.
That means the D can be restricted by function of y. And we can have x in terms of y, which means we are going to have dx dy. Okay. So y will be constant, and x will be restricted by the function of y. Okay. And the way we solve this, we call this is the iterated integrals, the double integral. We are going to solve the inside get the equations in the inside integrals, and then integral once more, and that's your result, final product. Okay. Okay. So basically, it's similar to the previous one. Okay, but the difference is this time we're going to have the constant is in y, and the curve will be x. Okay, it's having the curve.
Let me go through some examples to see the practicality on the double integrations. And sometimes
most problems in the double integrals, it will not have any, it wouldn't have any difficulty for the techniques, because if you remember calculus 1, we have several techniques. I think for the problem in double integrals is most likely the difficulty is to decide the point here. Okay. This will be the most challenging part. The integrations will be, I think, will be direct, and sometimes because we can use your calculator. You can use your calculator. So for computation, it will be not that much. Okay. But to decide this, that will be very challenging.
So I think we could start with this example 1. Okay, suppose that we have this. So we have the double integral
X plus 2y dA, and it's the information given is d is parabola 2x squared and 1 plus x squared. Okay. And I'm giving you the picture directly here, but sometimes the questions doesn't give you any visuals, so you need to decide the functions and you need to draw the function by yourself. Okay. If you are having problem drawing the area, then it will be very difficult. Okay. So first we have this y equal to x squared, and this is 1 plus x squared. Okay. So we have y as a function of x, right? So we could use that in the inside. And the outside, we need to find this point actually. We need to find the intersection point. So let me just draw, or maybe let me just write some steps that needed. So sometimes we are not given the picture. So first, usually, what we need is draw the area. Second, find the intersection if there are any. Between curves, which we can get from 2x squared equal 1 plus x squared. And then we get that the x squared is equal 1, which means x will be plus minus 1, which is true. So y will be, or the points, we can write 1 and 2, and also negative 1, 2, right? And after we draw the area, find the intersection, now we can set up the integral. Okay, so this is the first two steps.
Okay, now we have the constant x between negative 1 to 1, and then y will be, remember all the principles in the calculus 1 for the integrals top, bottom, left, right. This will be also same principles. So it will be top, it will be the 1 plus x squared, and this will be 2x squared. So we are going to take that in the endpoints of integrations. So we're going to write this for x and write the 2x squared and then 1 plus x squared. And then write the inside integrations. And this will be dy dx. Okay, I hope the integration parts should not be complicated, should not be difficult. We integrate with respect to y. We have x, so we have xy, okay? And then we have 2y, we're going to have, we multiply with half, right? And then we have y squared. I hope you get it. So we are going to have, this will be integral. I will use different color. So this will be xy plus y squared, okay, the results. And then plug in 2x squared, 1 plus x squared. And if you are maybe confused, what is the 1 plus x squared? This is actually for y, right? So let me also write, this is y equal, and this is dx. So plug in the y inside the equations. So this will be x and then 1 plus x squared plus 1 plus x squared, okay? And then minus x and then 2x squared plus 2x squared, okay? And close the bracket again, and then dx, okay? Because I think a few of you still have some difficulty for some simplifying the algebra. What I am going to encourage you is using the brackets. This will help. This is really helpful to avoid mistake, whether making the negative or positive. I think giving up the brackets, although it may makes your writings full of brackets, but it will help. It will help. For me personally, I have those personal issues when I try to solve equations, because I feel that I am confident, I know. Sometimes I make a mistake. Okay? To avoid mistake and make sure that we can convert easily, although maybe not really fast, creating this bracket will help. Okay, and then finally we can solve this. Simplify. This will be, so let me write like that. So this will be, or let me write in between. Okay, so this will be x plus x cubed, and plus this will be 1 plus 2x squared plus x4, right? And then let's say this is close bracket again. And for this bracket, we have 2x cubed plus 4x with power of 4, okay? But this is minus. I think we can write down all the things. And I think we can see this is x4, x cubed is with this one. So I think we can compute easily now. So we have x cubed, x4, I'm sorry, x4 minus, so minus 3x with power of 4. I will write in order. X cubed will be x cubed, minus 2x cubed will be negative x cubed. and then 2x squared, right? So no other variations. We can write down all the things here, and basically we integrate this. Okay. So integrating, we have -3/5 this will be half x squared plus x. Okay. If you have done some up till here, if you want to use calculator, that's okay. I think this will be simple enough to calculate. Or if you want to compute, I think it's okay. So -3/5 minus 1/4, so 3 half plus 1. I think we can, if you want to compute, we can compute. And then minus. Remember, we have -1, so every odd will be, or maybe let me just write with a, this will be -1, right? This is positive. This is negative. This will be also positive. And this will be a -1. Okay. So compute all of that. And this one becomes 3/5 and the same, right? So we can cancel. This one is the same, so cancel this. This one will be negative. Negative is positive, so not canceling. I think only, oh, the second one is cancelled, right? And yeah. So, oh, the second one, -4, and -1/4 is also cancelling. So 4/3 plus 2, right? Or no? Did I make mistake? 2/3? Which one?
The one in the right have minus in.
Correct, right? Because -1. Okay. Okay, wait. Plus. So what will happen if we have this with 4/3 plus 2? It doesn't seem anyone can find my mistake. But anyway, it should be 32/15. Okay, so yeah, that's why I don't like this. So I prefer to just write that and then confirm using calculator. 2/3 plus 2. Oh, the first one. It's not canceling. Right? Right? Yeah, why I'm canceling this? No. Okay, so plus, so -6/5. Okay, do not lose hope. Everything will be fine. So this will be negative 18 as 20. So negative 2 for 15 plus 2. This will be 30. So 30 over 15, so 30 over 15, yes. Okay. Okay. Okay, next example. Okay, I will go through some examples, some practicality until we get the idea, and I think I prepared some exercise in the backside, so we can have that as well. Okay, we have these questions, number example 2. So find the volume of solid lies under the paraboloid z equal x squared plus y squared and above the region D, okay, in the xy plane, which is bounded by y equal to x and y equal x squared. So this is the x squared, this is 2x. Okay, this is already given here in the picture. So first of all, if there is no picture, draw the functions. The second is finding the intersection. So first is always draw, the second is intersection. So 2x equal x squared, so x squared minus 2x equals 0. So x will be x equals 0 and x equal 2. So when x equals 0, y also 0, and y also x squared is 4. Okay. So we get all the points, and 0, 0, and 2, 4, and it's exactly, we can see that it's going to be intersection. Okay, now the next part is we are going to set up the double integral. We know the function. The function is the paraboloid. So let's set up the z equal the function of two variables. So set up the integral. We can have, let me write d is x. Let me write xy as in x is set from 0 to 2, and y is set from x squared to 2x. Okay, based on the picture. Okay, so you see the bottom part is x squared, the upper part is the 2x. Okay, so we've done that, and let z equal fxy equal x squared plus y squared. So the double integral will be, this will be fxy, so x squared plus y squared. Let me just write the a first in more general terms. So now we are going to set the integrations taking the x as the outside integral, so 0 to, and the inside will be the y. So y, let me write y equal x squared, y equal to x. Okay, and this will be the functions, x squared plus y squared. So this will be dy dx. Okay. Okay, we can start taking the integral that is on dy. So we can write outside as it is. Let me change the color. This will be x squared y plus y cubed over 3. And let me write, and input y equal x squared, y equal to x. And then we still have the x. And then let's input this too. Let me write here. So x squared 2x plus 2x cubed over 3 bracket and bracket. Okay. And then x squared plus x squared cubed we have the integrals, and we can put in all the integrations. I think I will have this 2x cubed. This is also x cubed, but 8 here over 3, right? And here we have x4, and then x with power of 6 over 3. Okay, we can have this become 14 over 3 x cubed, and then the rest will be as it is. So we can write this is negative x with power of 6 over 3 minus x with power of 4, and then plus 14 over 3 x cubed dx. Integrate once more. So this will be negative x with power of 7. This will be 21. This will be x with power of 5 over 5 plus this will be over 12, right? Or 7 over 2 x with power of 4. And then plug in 0 and 2. Okay, too many calculations now. So let me I think we can just focus on 2. So 2 with power of 7 is 128, right? 128. This is 32 over 5. It's 16. 112. Is this okay? Okay, I think we can turns up into calculator. Yeah. Even if you stop until here, if you are in exam, if you stop until here, it's still okay. We have overcome the challenges here, okay, so that's okay. Not a problem. I think not really that much importance. This will be should be equal to 216 over 335. Okay. Oh wait, this is not 2, this is 6, sorry. Okay, now in the other perspective, let me go back to the original questions here. In the other perspective, this is if we could see y equal x, right? In terms of function of x. We could also see if we could convert this in terms of function of y. For example, if we could take this in terms of, let's say this is going to be, it's going to be the x is half y, and here we can take the x is taking up the square root of y. Okay. So we can use this also to our double integrals, and we could choose y that is start from 0 to 4. Okay. So we could also, and this is the picture if you are interested to see how it looks like. It's actually like that. So we could use the d that is the y is from 0 to 4, and x is from half y, x, and then square root of y. Remember that we can see this graph as top down, or if we see from here, this is right left. Okay, so this could be works for both sides. We can use this function of y and function of x. Okay. Result should be the final result should be the same. So if we are using the function of y, then we could write the double integral now is 0, 4 as the outside, and then here will be the x, or function of y. So we are going to evaluate x first and then y. Okay. And you could integrate this, making it this will be x cubed over 3 plus xy squared. And then don't forget to plug in the endpoints. And this will be equal . So we have y 3 over 2 over 3 plus x, plus a y, so y half and y squared, so it will be 5 over 2, right? 5 over 2. And then we have negative y cubed 24, right? And then plus half y cubed, and then compute and evaluate with respect to y. So try to confirm. I think I will just skip this. This should be equal to the same result. Okay. Okay. Okay, maybe any questions? Okay, we take a break. Let's take a break for a while. Okay, let's continue. Okay, so we have established the setup for double integrals on the general region. And for example, if you have this case, we have set up the double integral of x, y, dA. We have line y equal x negative 1. And we have parabola y squared equal to x plus 6. Okay. So suppose that this is the picture that we can have, and we can basically make up two different ways. If the first one is we are going to set up the function of x. Okay. So we are going to have the y equal function of x. We can also choose if we want to make x in terms of function of y. Okay, so there's two different choices. If we are going to take the first choice using the function of x, that means, and of course after we get the points, the next thing we could do is we are going to set up. So suppose that the function of x, but notice that because we have this part of the curve, okay, so it's not easy to define the top and bottom equations, right? So if this is the top equations, the bottom equations will be this. So the best way to see this, to fit our equations, we need to split this becomes two regions. Okay, you could see it. Okay. So this part will be taking up okay. So we have region 1 and region 2. Okay. So the first region or if we could set up the function first, this will be negative square root of 2x plus 6 if it is going from negative 3 to negative 1. And then this will be x negative 1 if negative 1 is going forward to 5. So then the double integral, so negative 3 to negative 1, and this will be negative 2x plus 6, and this will be 2x plus 6, xy dy dx. Okay, and then the second region we are going to start from negative 1 to 5. Okay, to 5. This will be start from x negative 1, and then we have the square root of 2x plus 6. Okay, the last part there. This is the same, dy dx. This is pretty much we can do this, but of course if we see
dy, we could expect this will be y squared. This will be, we can express this and compute all of them. This is also the same, this is y squared, we can compute this. But because of we have this complicated much, right? It's much complicated. Then my suggestion, every time you see this kind of situations, okay, just like in your calculus 1, we have this, which is not easy to see the top and bottom. Then the best way, I think, to make it into function of y, because it's easy to see it's left and right, okay? Because if we could put this on the left and right, we can distinguish the region easily. Okay? So I think this way is much, much better. Okay? Both works, but the left one will have more works for you. Okay? And it's much more computations and calculations. The process is much more than the right. The right one, we can just focus on, this is the left, which is the bottom endpoints. This is the upper endpoints, right? So we could write that
as, and suppose that we have already got the intersections correct. Okay, so we can start the D. This will be from -2 to 4, and x will be from y plus 1 to half y squared minus 3. Okay. So we can write the double integrals as -2 to 4, and then write y plus, oh right, wait, I make it need to be, this one should be y plus 1. Okay, sorry. So this should be half y squared minus 3, and this is y plus 1, and we have, or let me just write xy dx dy. So we don't need to have two regions. So with this, I think it will be much more compact and supposed to be not as complicated as the last one, right? So integrate with respect to x will become x squared over 2, and x squared, we can input this minus this, right? So we can input this, become x squared over 2 y, and input so we are going to evaluate all of this, minus I think we can move the half. Let me erase half. And we can move half here, right? Okay. And this will be y squared plus 1 or plus 2y plus 1 y minus 1 over 4 y with power of 4 minus 3 over 2 multiplied by 2 is 3 y squared plus 9 and y. So this will be y cubed plus 2y squared plus y minus 1 over 4y5 plus 3y cubed minus 9y. Okay, this will be 1 over 4 y power of 4, 3 plus 1, 4, right? Plus 2y squared minus 8y dy. Okay, I think this is pretty much, we can check through calculators, I think will be better. This should be equal to 36, okay, 36, if not have any mistake. Okay, so let me overview. So the important thing in the double integral is not how your calculations will be, the final calculations, but rather to decide these endpoints. Okay? This is the challenge. So if you have like a question in the exam, determine this part will be much more percentage compared to the result itself. Maybe the result is not going to be exactly equal because some mistake here. But if you are still getting correct within the double integral, it's already 70 to 8%, 70 to 80%. Okay. Okay. Okay, next one, okay, I think last example for this part, because we have some other exercise as well. Okay, so next example here is already have the picture, but suppose that we only have this example, okay, this question. Finding the volume of the tetrahedron. Tetrahedron means it's similar to pyramids. Similar, but the base will be triangle. And it has bounded by the planes. There's this plane, and then we have the line equation on each part of the plane. So what should we do first? What we need to do is we need to get into the drawing side. And I think this one easy to draw in 3 dimensions, okay? Because we have the plane here, which we can check when one of them is 0, right? When one of them is 0. So we could pinpoint the positions. So first, we could draw the 3 dimensions. Okay, let me just put this out. So first is basically, if you see the x equal 2y and x equals 0, we could get the projections. Okay, we could get the projection, and also from here the x plus 2y equal 2. So we could set up, because we have the x equals 0 and z equals 0, we could set, so when z is 0, then x plus 2y is equal to, right? So we could set this line, draw into the 3 dimensions, and then we could have, when x is 0, then we have 2y plus z equal 2. Okay, this is also we can set up in yz axis. So we can set up in the yz axis, this is the line for the 2y plus z, and x plus 2y will be when z is 0, so this will be the line. Okay. This is the x plus 2y equal to. This will be for x equal to y. This will be for 2y plus z equal to. And then what else do we have? Oh, we can have also, because x is equal to y, we could substitute the plane. So it could be 4y plus z equal to, or 2x plus z equal to. Okay. So this is just to make sure that we draw the correctly 3 dimensions. Okay. And then, because we have this plane here, the other part that we need to also make sure is this area, because this will be, if we are going to set up this as our area for integrations, then we can also draw that in another picture. So let me draw here. So suppose that this will be 1, this is 0, this is 1. Okay, suppose that this is the projections. So suppose this is D, and if this will be the x plus 2y equal to, and this will be x equal to 1. And again, we can have 2 choices. We can use the x equal something or y equal function of x. But let me use y. Okay, let me use y. So this will be y equal half x, and this will be y equal 1 minus x over 2. Okay. And the plane, we can use the plane x plus 2y plus z equal to, and suppose that z is function of xy, we can write as z equal x, or 2 minus x minus 2y. Okay. So let's use this 2 minus x minus 2y as our function of 2 variables. So then the volume if you want to play with this, you can check using different projections. Okay. For example, if you want to check using the YZ projections, okay. For example, you can use YZ projection, which means you are going to use the Z part X. Okay. So this YZ. So for example, okay, just for so it's not always Z is function of XY. You can use different part of the variables as well. For example, if we are looking at using the projections, so projections YZ, so we are going to have this Z, Y, we have this, right? This triangle here. And then we can have the setup of our, so right here. So we can use X as our function of two variables, YZ. Okay, so this will be X equal 2 minus 2Y minus Z. The same terms, okay? And we can have the equations as it is. So we can have, but I think the problem with this one, we are going to have a, because it has these two trajectory, so we need to make sure that we have cover all the area, okay? But I think the best way to see this part using the Z, okay, as a function of two variables. Okay, now if we are using this projections, the XY projections, I will use X as our constant. So this will be 0 to 1, and the second one will be the Y. So Y will be start from half X until 1 minus X over 2. So compute as usual. I think we can compute as usual. This will be 2y negative xy and then plug in all the information here. So 2 and then minus this is x minus half x squared minus 1 over 4 x squared, and then the x. Close bracket the x. Okay, I think the last part here we can just compute, and then we are going to get the results. Okay, but the most important thing is to get the projections correct and finding each one of the restrictions of the endpoints. Okay, that's the most important. Okay, any questions so far? If no, maybe a little bit overview on this part. We can choose some of the questions here. Which one we can try today? Any requests? Any number? Which one? You think?
Whatever we 23.
23?
Yeah.
Are you sure?
With class. I don't want to see
Okay. Okay. Let's check number 23. Okay, now the idea in the double integral, okay, the function or the surface functions is not really important to be drawn. The focus now for the D, okay, the region D. So we are going to focus on determine this part, okay, in the graph. Okay. So first is maybe we draw that first to make sure that we are doing the correct one. So let's say we have the parabola x squared. Let's say this is the x squared. And then we have x equal 1. So x equal 1, let's say this is x equal 1 here. So this will be the x equal 1. So this will be D, okay? And of course the point here, although it's not proportional for x and y, should be 1, 1, right? Should be 1, 1. And then we could also imagine this will be 1, 0, this is 0, 0, okay? I think we get all the points, right? We get all the points that we need. We can make it into a function of y or function of x. But I think I will just taking the function of x because of the simplicity of the functions. So I will write directly here that it is going to be. So I will have x as our constant. So we are going to start from 0 to 1 and then start the line equations will be 0 to x squared, okay? So this is x equals 0, right? The line. Okay, so we start here. Okay, so how would be x squared? The line would be x equals 0. So we could start from 0 to x squared. And then we can immediately compute this. So compute dy. So we are going only integrating y. So cosine y integrate becomes sine, right? So x sine y from 0 to x squared, and we still have this is dx. This will be x sine x squared dx. And how to solve this? We can use substitutions method. So suppose x squared is u du 2x dx. Dx is 1 over 2x du. So we get half half, and this will be x will be cancelled, so sine of u du. So u is x squared, so still the same, right? And sine u will be cosine but negative, so negative cosine u, put 0 to 1. So this will be cos 1 minus cos 0. This will be equal to, this is 1, right? Cos 0 is 1. So I can reverse this, making it 1 minus cosine 1, right? Okay, that's it. Okay, I hope you can check the other question as well. I put two parts of the questions. This 23 to 28 and 31 to 40. Okay. So check that questions, and I think we can have another part will be next week. Okay. So next week, Tuesday, I will have review on chapter 14 and also continue this part a little bit. I think that will be for today. Okay. Is that okay? Okay, I feel you are looks really tired. Yeah. Campus life is tough. And you will get old quickly. Okay, let me get to the okay.